All right. Well, welcome back, folks. I want to apologize for yesterday. I don't know what happened to that video. I was trying to find it. Anyhow, I decided to go ahead and re-record the video here for you this morning. And so, um, hopefully, everyone had a good weekend, had a good 3 day break, and was able to kind of step away from school for a little bit. I just want to give you a couple of updates here. First of all, I would like to meet live on Monday. Um, so Monday, I'll post the Zoom meet again. So on Monday, I would like to meet live, just to kind of update everyone on what we'll be doing for the rest of the semester, for the rest of the week, and how we're going to end this semester. And so please come, please make sure then that you are available for during your particular class period, so that we can meet live. And I'll just take about 5-10 minutes of your time, just kind of see how everyone's doing, and then and again, like I said, update you on what we'll be doing for the rest of the week, and then how we'll deal with our final, and what you'll need to do, and how and I'll update you on the changes that I will make for the grading, and that way then you'll have an idea of what your grade what you'll what to expect as we go into the final week of the semester. Okay, so next Monday, please make sure then that you are checking in. Again, we will meet live for the first 5-10 minutes of class, and then I'll let you go so you can watch the lesson. Okay, and then we'll continue from there. Okay. All right. So with that, then let's go ahead and let's pick up with where we left off with on Friday. Okay, so I want to go ahead and finish up with these phase diagrams here, and we will start chapter 14. I want to go ahead and I want to talk about the gas laws, and how we work through them. Okay, and so let's go ahead and let's finish up with this here, and what we talked about here with the phase diagrams. What these phase diagrams are is they are graphs that we can use to follow then what happens to phase changes, what happens to substances when they undergo a phase change. A phase change is a change in phase, as the name applies, which, for example, then as the solid changes into the liquid state, that is a change in the phase of a particular substance. So as a substance undergoes a phase change, certain conditions have to be met up with. Okay? So we know, for example, how temperature affects the phase changes. Okay, so we know then, for example, as we increase the temperature on ice, okay, so as we increase the temperature on ice, it will start to change its phase. It will change from a solid to a liquid state as we reach a certain temperature. What that temperature is 0. Okay? So any temperature below 0 degrees Celsius, we know then that the water itself will exist in the ice state, its solid state. As we increase the temperature of that ice up to 0 degrees Celsius, we see then that the temperature, that the state that the water is in will remain in the solid state. But as we get to 0 degrees and then we start to pass that point, we see then that the ice starts to melt. It undergoes this phase change because it's moving from the solid state to the liquid state. Okay? And so we know then that that phase change can occur if we change the temperature. So as we continue on, as we continue to increase the temperature, we lose all of the ice. The ice completely melts as we go past 0 degrees Celsius, and we continue on towards room temperature at about 22 degrees Celsius. As we start to increase that temperature, then all of the ice is gone, and then we get the liquid state. Okay? And so once we get to the liquid state, then as we continue to increase the temperature, okay, and so we're seeing then this temperature dependency of phase changes. As we continue to increase the temperature, then we get to the point where the liquid water starts to change its phase. It starts to show signs of a phase change that we can actually see. That's the boiling. And so that boiling temperature, which we talked about, which is 100 degrees Celsius, as we get to that temperature, then we start seeing the liquid start to change its phase. We actually see it. Remember, evaporation, we can't see that happen. We can see the liquid level drop. So we always see vaporization with the liquid, but when we get to that 100 degrees Celsius point, we actually see the bubbles. We see the vapors form underneath the surface of the liquid, and so we actually can observe that phase change much more dramatically. And so once we get to 100 degrees Celsius, we see that phase change, and then we surpass 100 degrees Celsius. Eventually, we see that all the liquid gets transitioned into the gaseous state. And so if we look at that, we know then that the phase changes, we can get the phase changes to occur if we increase the temperature. So if you look at these phase diagrams, what you'll notice here, folks, if you look at the phase diagrams, what you'll notice here then is that along the x-axis, okay, what we have here is that the temperature is being recorded. So if you take a look at here, so let's go ahead and let's follow here what we have. Okay, we see then that as we increase the temperature, then we go from one phase into another. Okay, so let's go ahead and let's quickly review different parts of the phase diagram. Okay, so you have along the x-axis, you have the temperature. Along the y-axis, you have pressure. I'll come back to what this pressure means in just a moment. Okay, but that's what we have there. We have basically three lines, three curves that we have to follow. Okay, and each one of these curves here indicates then a particular a point along each one of these curves here represents a particular pressure, temperature, a particular pressure. But actually, any point along the any point on this graph here will represent a particular temperature and a particular pressure. Okay. However, I draw your attention to these lines because what I want you to see then is that what these lines do then is they separate three regions of this graph. Okay, three regions of this graph. A region, and so this line here, if you take a look at this, I'm sorry, this first line right here, okay, separates out then the solid state from the gaseous state. Okay, and this is the more generic graph, and I'll get to that in just a moment. This line right here separates out the solid from the liquid state. Okay, and then finally, this line here represents the division between the liquid and the gas state, and that's what we see here. Okay, so we see this first little curve right here separates out the solid from the gaseous state. This line right here separates the solid from the liquid state, and then this curve here separates the liquid from the gaseous state. So we have then each of these three lines separating out three regions of the phase diagram itself. So what can we do with this phase diagram? Well, let's go back then, and let's go ahead and let's consider what we have. I pointed out temperature. Okay, so let's go ahead and let's take a look at what we have here. Let's just pick a point on, and I'm going to pick an arbitrary point here on the graph. Okay? So if we pick this point here, this point represents then, if we remember how a Cartesian graph works, okay, this represents then a particular temperature and a particular pressure. And let's just say here, we'll call this temperature 1 and pressure 1. Okay, so this is going to be the pressure 1, and that's going to be temperature 1. So these are the coordinates at this particular point. If you look at that point, then that point falls in this region here that is the solid state. So that means then whatever this temperature is, whatever this pressure is, and so let's consider this here. This temperature here is well below 0. And we had just said then that at temperatures below 0, what state does water exist in? It exists in the solid state. So this point right here, which represents a certain temperature, okay, means then that as you increase the temperature, okay, so that represents a point, a temperature and a pressure that is at 0 degree, that's in the solid state. Okay, so if we increase the pressure, let's pick another point right here. Let's pick another point right here. Okay, so if you take a look at this point here, okay, if we take a look at this point here, we're going to see then that this represents a new pressure. Okay, but the same temperature, so the coordinates here will be different. This is going to be then, the temperature is going to be T1 still, but this is going to be P2. But if you notice at this point here, at this particular temperature and at this particular pressure, the water still exists in the solid state. Okay, so it's still in this region here in the solid state. Okay, all right, so let's go ahead then. Let's pick a third point. Let's pick a point right here. Okay, so we're going to increase the temperature essentially, keep the pressure the same. We're going to increase the temperature. So at T2 here, okay, at T2 and P2, what you'll notice is at this particular temperature and at this particular pressure, the water now is in the liquid state. It's in the, and so, I'm sorry, when we list water here, that means in water in the liquid state, okay? And we named it that way. So, all right, so at this particular temperature here, the water now has transitioned into the liquid state. Okay, so this point here, which represents a particular temperature particular pressure is a temperature and pressure in which the liquid exists. Okay, let's go ahead, keep the pressure the same. Let's increase the temperature a little bit more to this point here. Okay, so this point here represents a temperature at, we'll call T3. So now we have a different temperature, same pressure. Okay, and so at this point here, what we notice then is that this point here is in the gaseous state, the water vapor state. Okay, so as we increase the temperature, now we've gotten to a point where the liquid water is in the gaseous state. So what we've done here in this first line right here is we've diagrammed how changing the temperature changes the state. Okay, so we've just diagrammed the phase change here as it goes into from the solid to the liquid to the gas state by changing the temperature. Okay, so that's the temperature change. That's what we can do to the phase diagram, that we can see then the different states that exist as we change the temperature. Okay, but let me ask you this. Let me ask you to consider this. Okay, if we take this temperature here and let's take this point right here. Okay, let's take this point right here. So this is going to be then T2, okay, but the pressure is P1. Okay, this is T2, P1. At this pressure here, so the temperature is the same. At this pressure here, that means we've gone from a high pressure. So remember, pressure increases as you go up the y-axis. So we at P1 here, we are starting at a lower pressure but a higher temperature. What state is the water in this? What state is the water in at this particular temperature and pressure here? Well, it's in this region right here. So we have then water vapors. But if you notice here, as we increase the pressure up here, so the temperature is still the same, but as we increase the pressure, look what happens. The phase changes. The phase changes, which means then as we increase the pressure, now what happens is the water vapor is becoming liquid water right here. So what we can do with the phase diagrams is we can show then how we can not only change we can change the phases not only by changing the temperature, but by changing the pressure as well. Okay, so that's what we can do with the phase diagram, and that's what phase diagram shows us. Phase diagram shows us how the relationship between the different states of matter here, okay, but it also shows us how we can change those states by altering pressure and temperature. Okay, so we're all familiar with temperature changes, but now we can see then that the pressure changes also will cause a change in state as well. Okay, so if you look at this diagram here, then okay, if you look at this diagram here, this will help you. This will help us kind of understand how this happens. Okay? All right. So what we have here then is, let's go ahead and let's take a couple points here just to point things out to you. Okay. So we have then pressure and temperature again. So if you notice here, as we increase the temperature, and we're looking at the solid versus the liquid stage here. As you increase the temperature, and so what this arrow is indicating is an increase in temperature, we get a change from the solid to the liquid state, which we refer to as melting. Remember, we talked about this at the very beginning of this section here back on Friday. We said then that as you go from the solid to the liquid state, you get the melting to occur. You get melting to occur, and we get that done by increasing the temperature. By decreasing the temperature, we can get the opposite phase change to occur, which is freezing here. Okay, so melting and freezing occurs at this line right here. Okay, so as we increase the temperature past this line right here, then we get into the liquid state. As we decrease the temperature past this line, we get back to the solid state. Okay. So therefore, this line right here represents the boundary line between the solid and liquid state, which means that any temperature and pressure. Let's take a look at this point here. So this point here represents a temperature and a pressure, okay, in which then both states exist. Okay? Any point, any temperature and pressure along this line here represents then a dynamic equilibrium between the solid and the liquid state. Okay, you go past this point here. So if you decrease the temperature, let's say if you decrease the temperature, if you're going in that direction, just like this line indicates, you're going to get then a solid. If you increase the temperature and go in that direction, you get the you get the liquid. Okay. However, as a temperature and pressure right on that line then represents then an equilibrium state between both the solid and liquid. You have both existing at the same time. Okay. All right, so that's what the line here represents here. So same thing as we go through here, if we take a look at this here, look at this particular line here. As you move past the line, as you increase the temperature past that line, you get vaporization. You go from the liquid to the gas state. As you decrease the temperature, you get condensation because you go from the gas to liquid state. But any point on that line, the temperature and pressure there represents then an equilibrium between the liquid and the gas. Okay, so that means then both exist at the same time. Okay? And then finally, if we take a look at this last division here. So as you increase the temperature past this line right here, you get sublimation. Okay, that means a solid, remember, converting directly to a gas. And as you go in the opposite direction, you get deposition, which means then any point along this particular line here, which represents a temperature and a pressure, okay, then you can get then what's called, you get the equilibrium between the solid and the gaseous state. Okay? All right, so with that said, let me just highlight a couple more points here before we go on. I'm running a little low on time here. You get this triple point here. Okay, remember we talked about this triple point. I had mentioned this back about a week ago. Okay? At this particular point here, if each one of these represents an equilibrium between each one of these states here, so this point here represents an equilibrium between the solid and liquid, meaning that both exist at this particular temperature and pressure, we have both the solid and the liquid existing at the same time. Any temperature, again, past this point, you only have liquids. Any temperature below this point here, you only have solids, and so forth. Okay? And so that means that at this particular point then, at this particular temperature and at this particular pressure, all three states exist in equilibrium. And we said that that's a triple point. That's what we refer to as a triple point, and that is a unique point. That is a unique temperature and pressure for different substances. It's different substances will have different triple points, and so that means then at a particular temperature and pressure, all three states of that particular substance will exist in equilibrium with one another. Okay. All right. So we see then in this particular graph how altering the temperature will give us the different phase changes. Okay, so we'll cause the different phase changes. However, I want to also point out to you, and we talked about this, I want to point out to you what happens when we change the pressure. Okay, so let's go ahead and let's consider what we have here. Okay, okay, so let's take a look at what happens. So we've highlighted the different melting and freezing here. Can you get melting and freezing to occur if you change the pressure? Well, let's take a look at this here. Okay, so if you, let me highlight this here again. Okay, so we just said that melting is the change that occurs when you go from the solid to the liquid state. Okay, so let's consider this here, and this is going to be a little bit more difficult for me to highlight for you, but let's go ahead and consider this here. Okay, so let's go ahead if we can consider going from this point here downward, and I'm sorry, that's a little bit off here. If you take a look at that point there, we are here, at this point here, we are decreasing the pressure. Okay, we are decreasing the pressure rather than increasing the temperature. So here we are decreasing pressure. And if you notice, as we drop the pressure here, we are going from the solid state to the liquid state. We are melting a solid right here. We are melting a solid here without changing the temperature. We are causing the melting to occur here by decreasing the pressure. So by changing the pressure, we can also cause this phase change to occur. Similarly, if you increase the pressure, so let's go ahead and consider what we have here. If you increase the pressure in the opposite direction, okay, so let me go ahead and draw the line here, and this is going to be kind of off here, okay. If you increase the pressure there, if you take a look at that, by increasing the pressure, okay, you see then we move from the liquid state to the solid state, which is what we refer to as freezing. Okay. And I think it becomes much clearer when we talk about liquids and gases here. So let's go ahead and map the pressure changes for the phase changes for the liquid to the gas state. Okay, so let's go ahead then and look. Let's see what happens here. Okay, when we change the pressure. Okay, so if we take a look at this here, okay, we go from, let's decrease the pressure. Okay, so we decrease the pressure right there. Okay, so as we decrease the pressure here, look what happens, folks. As we decrease the pressure here, we go from the liquid to the gas state, and we refer to that as vaporization. Okay. So we can cause a phase change here from the liquid to the gas state, which is vaporization. Remember, liquid to the gas state is vaporization by, again here, decreasing the pressure, not increasing the temperature, folks. Remember, here the temperature stays constant. Okay? Temperature is constant here, but we are dropping the pressure. We're decreasing the pressure here, and we get the phase change. Conversely, if you take a look at this, folks, if you go in the opposite direction, let's go in the opposite direction. Okay? So let's go ahead then and let's increase the pressure. Okay? As we increase the pressure at this point here, if you see this, as you increase the pressure here, what do we get? We have the gas converting into the liquid state, which is what we refer to as condensation. Okay, so condensation there occurs when you take the pressure and you increase it. And so we see this effect here being much more dramatic with the liquid to gas change, or gas back to liquid change, than we do with the solid to liquid, but it can happen. And so what, again, like I wanted to point out to you then, is that we can follow the phase changes here, okay, and see how temperature and pressure affects the phase changes. Okay? So not only temperature, so we see here temperature affecting the phase changes, but now we also see then pressure changes can also affect the phase changes as well. Okay, all right. So that's what the phase diagrams allows us to do. Okay, and so let me go ahead and get this out of the way here. And so make sure you keep this in mind, okay, and and be able to interpret these phase diagrams in terms of how pressure and temperature, both pressure and temperature, affects phase changes as well. And what lastly, what I want to point out to you is that when you take a look at these phase diagrams can get more complex. But typically, what we see then is these phase diagrams will be unique for different substances, okay? Because different substances will have different melting points, different boiling points. And so with that said, then, well, when we take a look at this, we can use the phase diagrams also to figure out which substance we have here. We know a little bit more, okay? All right, so with that said, then, if you take a look at this here, again, along each one of these points, and I'll wrap up this here, we have then what's called the normal boiling point. What do we refer to as the normal boiling point? Remember, normal meaning then the normal melting and boiling point. Sorry, normal boiling point meaning then that the pressure and the temperature at which a liquid changes, okay, from a liquid to a gas, or a gas to liquid, okay, at 1 atmosphere. Okay, so this is 1 atmosphere of pressure here. And so hopefully, like I pointed out to you, this phase diagram, you can identify the substance that this phase diagram is representing based on the boiling point and the melting point here. What substance then melts at 0 degrees Celsius at 1 atmosphere and boils at 100 degrees? This is the phase diagram for water. Okay. All right. So with that said, then let's go ahead and let's finish up here. That is it for, I'm sorry, one last one here. One last one here before we finish up. Okay, one last one here. If you take a look at the normal boiling point here, so here's 1 atmosphere. This is obviously not water because this represents the normal melting point for this particular substance, okay, which is at negative 78.5. So this is negative 78.5 degrees Celsius. And if you take a look at this here, it doesn't even have a normal boiling point. Okay, so this liquid here is, this particular substance here is carbon dioxide. Okay? And so if you can compare this particular phase diagram to the one we saw for water in the previous slide, at the normal, so here is the normal melting point. And how do we know that it's a melting point? Okay. I'm sorry, I'm gonna put this in quotes here, okay? Because this is actually melting. Remember, melting is solid to liquid. This is the normal sublimation point for this particular substance. Okay? And so the phase change that occurs at 1 atmosphere is the phase change only between solid and the gaseous state. You don't get at 1 atmosphere a solid to liquid state. So therefore, this is very different from the phase diagram for water, because carbon dioxide If you notice here, the liquid form, if you follow the line across here, does not exist at 1 atmosphere of pressure. Okay, at normal at sea level pressure here, we either get the solid state or the gaseous state. Okay, so again, we can use these phase diagrams to kind of characterize and identify the compounds and the substances as well. Okay. All right, so with that said, I apologize. It went a little bit longer than I was hoping, okay, but that's okay. What we're going to do then is tomorrow, what I'll do this tomorrow, then we'll start the Monday. After we meet, I'll let you go, and then we'll talk about the gases at that point. Okay, so make sure you have the fit labs done, and then what we'll do is we'll use the fit lab to talk about the gases. Okay? All right, very good, folks. I will have a good weekend, and I will see you live on Monday.